Okay, well, why don't we make a start? I was reminded that I had not introduced myself. My name is Barry Green, and as I don't live on campus, if you want to contact me, I've got an email address, barryjohngreen, all one word, @yahoo.com.au. And once again, I said that for the lecture hour after this lecture, I'm in room 461. It's the visitor's room on the 4th floor, and I'm there if you wish to see me, okay? Okay, so what did we do last lecture? In our first lecture, we talked about the discovery of the nucleus by Rutherford, the nuclear model of the atom, nuclear structure, discoveries of the proton and neutron, talked about nuclear mass, and then the equivalence of mass and energy, and we finished up with the very important topic of binding energy. The energy that binds the nucleus together. We talked about the nuclear force, of course, which provides that energy. So today we've got three topics, basically. We've got nuclear stability. Not all nuclei are stable. We'll talk about nuclear reactions, transmutations, and particular cases of that, so-called fusion and fission. And then we'll talk about radioactivity, something you probably know about from your experience maybe. Alpha, beta, and gamma decay, which goes to make up radioactivity. We'll talk about the rate of decay, the half-life of a radioactive nucleus, and so on, and decay series. So let's start off with the talk of nuclear stability. For light nuclei, essentially the stable nuclei have an equal number of neutrons and protons. The capital N, you remember, is the number of neutrons in the nucleus, and Z, the atomic number, is the number of protons in the nucleus. And if they're equal, then of course the mass number they're equal to half the mass number, because the mass number A is just the sum of Z and N, the sum of the protons and neutrons in the nucleus. However, when you get a little bit, when you have more protons, you go up a little bit in proton number, the electrostatic repulsion starts to get very significant. In other words, the nucleus tends to blow apart because of the repulsion, and so you need more neutrons, which have the effect of reducing the distance between the protons, increasing the distance between the protons, and so you need more neutrons to stabilize them against the greater Coulomb repulsion, and at a certain stage, which is given by your textbook as this Z equals 82, nuclei are intrinsically unstable. You can tap them a little bit and they will do things. So here's the curve, if you like, of nuclear stability. Up the axis here on the left, we have the number of neutrons, and on the horizontal axis, we have the number of protons. And as I said, for low Z, for low numbers of protons, stable nuclei essentially lie on this line, which is the line of equal numbers of neutrons and equal number of protons. But as the number of protons increases, stable nuclei have to have more neutrons. And so instead of lying on the line of equal neutrons and proton number, they veer up on the side. The trend is to having more neutrons. So now we're in a position to talk about nuclear reactions. What is a nuclear reaction? Well, it's a reaction between nuclei, and it's essentially a rearrangement of nucleons. The nucleons, remember, are the particles that make up the nucleus, and what happens is there's a transmutation. Now, what does this long word mean? It just means changing one chemical element to another. It can be natural, as in this particular case, which we've used radium giving off an alpha particle and leaving another nucleus called radon. And this is a naturally occurring radioactive decay by an alpha particle, where the radium nucleus gives up the alpha particle and the remaining product is a radon nucleus. Now, we're going to pause there a little bit because all the nuclear reactions are characterized by two things. One is the charge is conserved. So you've started on the left-hand side with 88 positive charges, 88 protons. You've produced a helium nucleus with 2 protons, and you're left with a radon nucleus with 86. And you see that 86 plus 2 is 88. So very first thing on any nuclear reaction that you write down or that you look at, you must have the number of charges is conserved, okay? But equally, the number of nucleons has to be conserved. So the number of nucleons, protons and neutrons, has to be conserved. So you started off with 224 of them, and you've got a helium nucleus which has 4 nucleons, 2 protons, 2 neutrons, and you end up with 220 on this side. And if you add the superscripts there, 220 plus 4, you come back to there. So this is critically important, of course. Whenever you see a nuclear reaction on the board, just check it's got to have conservation of the charge number, and it's got to have conservation of the nucleon number, okay? And that's what that underlined blue sentence says. Now, often in a reaction such as this, a nuclear reaction, energy is released as the kinetic energy of the products. Okay, and any photons, if any radiation was released during this particular reaction, then you'd have to add up that energy as well. And of course, energy would have to be conserved. Mass energy would have to be conserved. And we're going to do calculations like that. So I've got 3 examples of the transmutation of an element. Here's the first one. The uranium-238 here, and you know uranium-238, it has 92 protons. There you see them. And therefore, if it's got a mass number of 238, you do the subtraction and you find it's got 146 neutrons. It decays, giving off a helium particle, 2 protons, 2 neutrons. And it decays to give a thorium nucleus, which has 90 protons and 144 neutrons. And if you add those up together, it gives you thorium-234. Quick check, 234 plus 4 is 238, 90 plus 2 is 92, okay? So this is the natural decay of uranium into thorium, where an alpha particle is emitted. Now, the thorium itself is radioactive, but it decays differently. Here's the thorium-234 with 90 protons and 144 neutrons, and it decays to something called palladium with 91 protons, more than this one had, and a certain number of neutrons. And on this side, another product is an electron. Now, it's not an orbital electron. It's not from the outer shells of the atom. It's a nuclear-derived electron. Comes from, essentially, you can see, from the decay of a neutron. Anyway, we'll talk about that in a minute. This is so-called beta decay, and this is a beta particle. Thorium naturally transmits to, not palladium, proactinium, where a beta particle is emitted, and the electron is written in this way. It has a negative charge, the same value of charge as that on a proton, but negative. And the 0 indicates that the electron mass is negligible compared to the nucleons. It's not saying that electrons have 0 mass, but in this sort of analysis that we do, we regard it essentially as 0. Subscript -1 is the electric charge. Okay, so the third thing is artificial transmutation, which this was the famous reaction that was carried out in the laboratory by Rutherford and his team. And they fired alpha particles from that radioactive decay of radium at nitrogen gas, which has the nuclei have 7 protons, 7 neutrons, and they managed to obtain hydrogen, a proton, simple hydrogen, and an oxygen nucleus. Now let's just check that everything is all right. So mass number 14 plus 4 equals 17 plus 1, and charge number 7 plus 2 is 8 plus 1. So everything in the garden is okay. So an alpha particle fired and impacting on a nitrogen nucleus transmutes into oxygen and hydrogen. And we've done this conservation. So here we are, we're seeing the transmutation of elements, which, if you read a little bit about medieval history and so on, the alchemists wanted to change lead into gold and so on. And what they didn't realize, it was going on all about them. Okay, so here's a little question. The answer was on the previous slide. So is anybody going to tell me atoms can transmute into completely different atoms in nature, laboratories, both A and B, or neither A and B? Who's going to give me that one? Good on you. Okay, it occurs in nature, in labs, and as far as we now know, throughout all of space. Now, here's a little bit more difficult. You have to do a little bit of simple mathematics for this. An element emits a beta particle, that's an electron, negative charge. And its product then emits an alpha particle, which has 2 positive charges. What's the atomic number of the resulting nucleus? Okay? And you have the 4 usual. There's no change. -1 or -2. Anyone like to hazard, or none of the above? Anyone like to hazard a go at that? You lose an electron, that's a negative charge going. So it's given you a surplus of 1 positive charge. Then you lose an alpha particle, which takes away 2 positive charges. So +1 -2, what do you think? Good on you. Okay, so there's the thing. The beta emission increases the atomic number by 1, and then the alpha emission decreases the atomic number by 2. So it's +1 -2, and fortunately we all get -1. Now, here's the sort of calculation that we are now set up to do. Just as in the binding energy calculations we use the equivalence of mass and energy, we can do the same for nuclear reactions. For instance, we've got a reaction up here. We've got a proton hitting a carbon-13 nucleus, and the result would be, according to our rules, 7n13 plus a neutron. Now you see that the number of nucleons is 1 plus 6 gives us 7. Oh, sorry, the 1 plus 6 for the atomic charges, for the atomic number, is equal, and 13 plus 1 gives 13 plus 1. So everything that's written there is okay, but can it occur? And in fact, we've given a little bit more information. We clearly need some energy to make this go, and we're going to bombard it with 2 MeV protons. So we're putting 2 MeV amount of energy in. So how do we do this calculation? Well, what we're going to do is we're going to add up all the masses on the left-hand side and the right, and we're going to compare it with the masses on the right-hand side. And we're given certain things. We're given the atomic mass of C13 in mass units. We're given the atomic mass of nitrogen-13, and we're given the masses of the nucleon as a proton is that, and the neutron is slightly more than the proton, which we'll talk about in a minute. And the mass of the electron is this, and this is quite important because when you're given atomic masses, if we're doing a calculation involving nuclei, we need to take away the electron masses. So for instance, we're told that the atomic mass, says atomic, of C13 is this. So that's the mass of the nucleus plus the 6 electrons that are orbiting it. So if I look at the left hand, the reaction will proceed if it's exothermic, if energy is given out, or even if energy is required and there is sufficient energy available. So unfortunately, I have to do my calculation on the next page. So the left-hand side is the C13 atomic mass minus 6 electron masses plus the proton mass, so that the total mass of the left-hand side, without the mass equivalent of the energy so far, is this, 14 something something atomic mass units. Now, if I do the right-hand side, I take the nitrogen and I remove 7 of its electrons, because this was an atomic mass, and I add on the neutron, then I get this value. And you find that the right-hand side equivalent mass is greater than the mass on the left-hand side. And that's what this says. It's equivalent to a certain amount of energy. Remember, we did the calculation in the first lecture that each atomic mass unit was roughly equal to 931.5 MeV. So this small mass difference to go from the left-hand side to the right-hand side requires an energy of 3 MeV, the energy equivalent mass. So it's more than we've got available. We were told we only had 2 MeV for the protons that we fired in, but we really require 3 MeV to make that reaction go, so the reaction cannot occur. Now, that's a sort of standard type of question or calculation that you might be asked to do. And all it is just adding up the left-hand side, adding up the right-hand side in masses, taking the difference, what's the energy involved, and away you go. So now we're in a position to calculate the energy released in a couple of very important processes. One is the so-called fission, or breaking apart of heavy nuclei such as uranium-235. Now, when we come to talk about fission in a couple of slides, we'll find that there are many different reaction paths that this fission can take. But on the average, the final mass of the products of this fission is less than the initial mass by about this number of mass units. So, and I've said here very crudely that each atomic mass unit is about 931 MeV. So calculate the amount of energy per fission and the fission of 1 kilogram of U-235, which is the sort of thing that you have in a reactor, in a fission reactor. And of course, if you want to know the number of nuclei in a gram molecule, then you need this number, Avogadro's number. That's the number of molecules in a gram molecule of the substance. Okay, so the energy equivalent of this mass loss in the fission is 0.21 times about 931, gives you so many MeV, and in this particular case I've converted it to joules. So each MeV is 1.6 by 10 to the minus 13 joules. And so this is the amount of energy on average for each fission, the fission of each nucleus. So of course we have to find out in 235 grams, or sorry, in 1,000 grams, in a kilogram of this stuff, we have to find out how many nuclei there are, and then we just multiply that by the amount of energy that is given up in each fission. So if we have 235 grams, that's the molecular weight of U-235, we know that there are so many molecules, or atoms, sorry, so that 1 kilogram of U-235, there is 1,000 over 235 times Avogadro's number, or 10 to the 23 times this number of nuclei. So in spite of the fact that each fission produces a very, very small, apparently very, very small amount of energy, wow, the number of nuclei that are doing that is very large, and so you have this figure, that's the amount of energy from the fission of a kilogram of uranium-235. And just to point out that that is really a significant energy, it's equivalent to burning 3,000 tons of, or 3,000 tons or 3 million kilograms of coal. So fission, very, very energy dense. There's a lot of energy involved, which is, of course, why we have reactors. Now, let's talk a little bit more about these two processes, which are nuclear reactions. and transmutations, if you like. If light nuclei, such as the isotopes of hydrogen, that is deuterium and tritium, so there's one deuterium-2, one tritium-3, they're hydrogen because they have one proton, but they have different numbers of neutrons. If they're forced together under certain conditions, we can produce a helium nucleus plus a neutron. And if you remember that figure that we showed where we had binding energy per nucleon, and it rose up to a flat bit of iron and then went down a little bit to uranium, you notice that these things on this side, or this has a higher binding energy per nucleon than these two on the left-hand side, and therefore you expect this to be energetically favorable. You're going from a less stable to a more stable state. Fission, on the other hand, is entirely the complementary process whereby heavy nuclei are forced to break up. Fission, breaking apart. Fusion, pushing together. The resulting fragment nuclei are energetically more stable. They have higher binding energies per nucleon than the original nucleus. So you go from uranium, you cause it to fission by firing a neutron at it, and it breaks up. There are many different ways it can break up, but this is sort of standard one, krypton and barium, and 3 neutrons. And you can see here that if these neutrons went on to give more fissions, you have what is called a chain reaction, about which we will speak in the future. So this is the curve. I'm sorry for the quality, but this is the curve that I was talking about, the binding energy per nucleon up this axis from 0 to about 8, a little bit over 8. And here is the mass number of the nucleus. And you can see that if you have deuterium and tritium fusing together, they produce helium, which has a higher binding energy per nucleon. And if you cause uranium, which is up here somewhere, to split, it moves up here to barium and krypton, and that also has a higher binding energy per nucleon than you started with. So on this side of this line, if you like, the point at which the nuclei have the most binding energy per nucleon, you have fission on this right-hand side, and you have a possibility of fusion on this side. So now let's do the explicit calculation for that deuterium-tritium fusion that I showed you. So we have the atomic masses of deuterium and tritium, and of helium-4, which is the alpha particle, and a neutron. So the sum of the things that are reacting, the deuterium and tritium on the left-hand side, you can check me, I hope, is correct, 5.03 atomic mass units, and the sum of the helium and the neutron on the right-hand side is less. So where has that mass gone? Energy, okay? The mass is lost from moving in that reaction from left to right, so energy is released, and if you do the calculation, you find out it's 17.6. It's equivalent to 17.6 MeV, because I converted the atomic mass units by multiplying by this 931.5 MeV per mass unit. And so you get energy that appears as the kinetic energy of the alpha particle and the neutron, and that amount of energy is 17.6 MeV, which is a figure which, if you're in that game, which I was, you get to know very well. So let's do the other calculation, which is that of the breaking up, the fission of uranium. And once again, I give you all the masses. Here's uranium-235, nuclear mass, krypton, and barium, and neutron. So the sum of the uranium and the neutron on the left-hand side is a certain number of mass units, and the sum of the krypton and the barium on the right-hand side is that, and you find out that mass has been lost again. So that the reaction goes from left to right, energy is released, and the amount of energy released is just the difference in the mass times the conversion to energy, and you find out you get 178.4 MeV, a lot of energy. Okay, so those are the sorts of calculations I would expect you to be able to do. Would give you the atomic mass units that are involved, and you have to do the additions and subtractions. So here's the case for fission. You start off with a heavy bound nucleus, and when you split it up, you find out that the constituents are lighter than what you started with, and the difference, of course, is the energy that's released in the nuclear reaction. So now we're in a position to talk about radioactivity. What do we know about radioactivity? Well, it's in the news, of course, a lot just these days, as the federal government is trying to find a place in Australia to dump so-called radioactive waste. So what's radioactivity? It was what happened about the turn of the, as the 20th century got underway. This guy, Henri Becquerel, discovered that there was some sort of radiation coming off from uranium, and it affected a photographic plate. That's how he first discovered it. He left a bit of uranium in a drawer, and next to it was a photographic plate, and when he pulled out the photographic plate, it had been partially exposed. So this radiation was, of course, of interest to nuclear physicists, and the Curies, Marie and Pierre, started studying radioactive things that gave off this sort of radiation, and they found radium, and they found that this radiation was not just from uranium, but from other materials as well. They found it could ionize air. That meant that you could conduct electric currents through air once the radiation from this stuff had affected the air, and it could be deflected by electric and magnetic fields. So that was a big discovery. And they found out that we now know that this ionizing radiation is emitted from unstable nuclei, which are decaying. So there's decay. What we call radioactive decay, and that is transmuting to another nucleus. And three types of decay, or three types of radiation, are involved. One is decay with alpha particle emission, so-called alpha decay. One is called beta decay, with the emission of beta particles, which we'll see are electron-like. And one is just radiation, gamma radiation, which we know now is the smallest wavelength electromagnetic radiation. So it's the process of nuclear decay, so-called radioactive decay. It's nothing new. It's been going on since time zero. We'll talk a little bit about how the universe got put together, but once the heavy elements were created, they were unstable, and then they started fissioning or radioactively decaying right from that moment. We owe the wonderful geothermal power that used to heat HBF Stadium pool and to provide some energy to the university air conditioning. That heat that comes from the ground is nuclear. We call it geothermal energy, but what it is heat that's coming to the surface from the radioactive decay of nuclei in the Earth's interior. So we've got radioactivity all around us. Maybe in the last lecture I'll bring in a Geiger counter, which we'll talk about. We'll talk about detectors, and I'll find out how radioactive we are now. We have some background radiation here, and then I might do a little test on fire detectors. This thing up here, that's got a little radioactive source in it, and things like that. And you'll see that radioactivity is all around us. It's natural. So let's find out what we've got. The answer I've just given you, radioactive decay of nature's elements, it occur in soil, air, interior, all of the above, indeed. So this slide indicates the three different sorts of radioactive decay. The alpha particle, which are just charged helium nuclei, And of course, that means they're positively charged to protons, to neutrons, and so they can be deflected by magnetic fields. Equally, the electron-like decay, the so-called beta decay, is negatively charged and so can be affected by a magnetic field. But the third type of decay, which is electromagnetic radiation, has no charge and therefore cannot be affected by magnetic fields. Oh, and I mean, they've got pretty little pictures. This shows you that it's electromagnetic radiation with a wavelength and so on, and this shows the particles that are involved. And here the source of the radiation, if you like, is in a lead block to shield the people who are standing around it. So let's talk a little bit about alpha decay, and we've used alpha decay, or I've mentioned alpha decay many, many times, because in the early days, the radium that people had found and the Curies had discovered was a wonderful source of projectiles that the physicists could use in investigating matter. So alpha decay, good example of it, is radium gives off an alpha particle, and what remains is radon. And you see once again for a nuclear reaction, the number of positive charges, 86 plus 2, is the same as 88, and the number of nucleons is 222 plus 4, which is 226. So we've written it down correctly. What happens, though, in alpha particle decay is that the atomic number decreases by 2, okay, because you've produced this alpha particle. And similarly, the number of neutrons in the nucleus has reduced by 2, and that means the mass number has reduced by 4. Okay? With me? Now, it occurs for large nuclei. The strong interaction has short range, fails to bind the big nuclei against the strong Coulomb repulsion of the protons, and that's why these nuclei find it easier to get more stable by belching out an alpha particle. So now let's talk about beta decay, which is slightly more complicated. But beta decay here is a good example of it. 6C14 decays into nitrogen-14 together with an electron, -1. So -1, this is the charges, 7 minus 1 gives you 6. And the number of nucleons is the same. Now, I've got a little particle over here called an antineutrino. Now, I just put that in for correctness. When you have to analyze these things in terms of angular momentum and so on, you find that another particle is needed, and somebody quickly noticed that very early on, but it took many, many years before this fellow was discovered. But there's the beta decay. An electron is produced. And it occurs when you've got too many neutrons for the number of protons. It increases the atomic number by 1 and decreases the number of neutrons by 1, but the mass number, sum of nucleons, remains the same. And it is extremely important, even though we're speaking about electrons, to be clear. This is nothing to do with the orbital electrons of an atom. But just to confuse the issue, we'll talk about some in a minute. So free neutrons are actually unstable. If I had a free neutron, after some time, it undergoes a decay into a proton and an electron. There is another sort of beta decay, but in this case, it's a beta plus, not a beta minus decay. This is the antiparticle to an electron, a so-called positron. Now, I don't know whether any of you are unfortunate enough to have PET scans, but a PET scan is a positron emission tomography setup, and we'll talk about positrons, and maybe even when we get there, we'll talk about PET scans. So this positron exists, important, and this is one way for nuclei to beta decay, except instead of decaying to the usual E minus or beta minus, it decays to a beta plus or an E plus, and that's the positron, and the antiparticle of the antineutrino is just the neutrino, and that's required from angular momentum points of view. So here you have neon. decaying to fluorine, a beta plus, a positron, and a neutrino. And you see that I have the number of charges is the same, plus 1 plus 9 is 10, and the number of nucleons remains unaltered. So there is a third sort of beta decay, which, I mean, we just should know that these exist, is an electron capture in which a nucleus absorbs an orbital electron, one that's fairly close to the nucleus, of course, and that's called K capture because it's usually from the K shell. This process decreases Z by 1 because you've put an electron on the nucleus, and it increases the number of N, the number of neutrons, by 1 because that electron becomes a proton. So beta decay is quite complex, or more complex. It's caused by something which we won't speak about afterwards, but it's caused by something called the weak force, or the weak interaction. Neutrons were postulated in these decays, but only discovered 26 years later. And you find that you have to propose these particles to conserve energy, momentum, and angular momentum. And indeed, later on, they were discovered with all the right properties. Ordinary neutrino is emitted with an anti-electron, which is a positron, and an anti-neutrino is emitted with an ordinary electron. So beta decay, there's a little bit more to know about. And this is just the general picture from your book. If you decay here, proton form from a neutron, you lose the neutron, and that's the beta particle, the beta emission, and then you're left with this fellow, and then the alpha particle is emitted. That's alpha decay, beta decay. And a neutron near a proton is stable, but neutron by itself is unstable. And this just says you can have alpha particle emission, alpha particle decay. So let's see what this little question is. An atom that emits an alpha particle or beta particle becomes an atom of a different element always, may become an atom of a different element, becomes a different isotope of the same element, increases its mass. Who's going to hazard a guess on that one? Shaking of the heads. Nobody prepared to give it a go? So this is where I said that all the alchemists who had been working for years to try and convert lead into gold, which of course was far more valuable, it was going on all around them, and they didn't realize it because, of course, they didn't have the ability to look at nuclei. They didn't even know nuclei existed. So let's talk about the third decay, gamma decay. So this is decay of a nucleus from an excited state to a lower energy state. It's a bit like an atom, if you like, where the electrons go from a higher energy state to a lower energy state and give out photons. This is photons of gamma rays when the nucleus goes from a higher energy state to a lower energy state, and there's no change in the atomic number or the mass number or the number of neutrons. Gamma rays typically are from nuclear processes compared to their higher wavelength cousins or brothers or sisters, whichever you like, which are usually from atomic electronic processes, right? Gamma rays have lower frequency. The X-rays have lower frequency and higher wavelength. So the gamma rays are very, very high frequency. They're photons. H times the frequency are very high, but low wavelength, very low wavelength. And here's an example of a gamma decay. We've got, say, boron 12, and it decays to carbon 12, but it can do so in a couple of ways. It can either give it through beta emission, or else it can go via an intermediate step where the carbon 12 nucleus is excited. That's what that little asterisk means. And then that carbon 12 nucleus, which is excited, de-excites with the emission of a gamma ray. And there's a whole lot of spectroscopy to do with this sort of transition. Just as there's spectroscopy in terms of spectral lines that we look at. So there's so-called gamma ray spectroscopy looking at decays such as this. And this state in here, this excited state, may be metastable, which means it lasts for some time. And that's important in things like lasers. Lasers have to have, lasing mediums have to have metastable states. And you don't need to know about isomers, okay? So excited nuclei sometimes decay by internal conversion, where they interact with an orbital electron and ejecting it with kinetic energy, so that the emitted gamma ray would have had that energy. Well, that's a little wrinkle as well. But gamma rays, remember, no charge, electromagnetic radiation. And there we are, that reinforces the matter. The light that you can see me by is in a very narrow band, 400 to 700 nanometers. The X-rays are a lot smaller wavelengths, and the gamma rays extremely small wavelengths, but the frequency goes up, as you can see, the number of waves per second. Okay, so you must know this one, which is, these is the nucleus, the helium atom, an alpha particle, a beta or a gamma. All the different forms of helium, please tell me. Alpha, great. Now, which of these is actually a high-speed electron, an alpha particle, a beta particle, or a gamma ray? All are high speed. What's the answer there? B, exactly. It says here D may be true, but doesn't directly answer the question. So a high-speed electron, beta particle. Okay, now the last little bit we've got to do is rate of decay and half-lives and so on. Now, nuclei, radioactive nuclei, decay at random, so it's a random process. The rate of decay is its activity. So I'm going to represent it. I don't know how much calculus you've had, but this is the rate of change of the number of radioactive nuclei per time, dN by dt. And we found, or it is found, that rate of change is negative because the number of radioactive nuclei is decreasing as they decay, but that rate of decay is proportional to the number of radioactive nuclei that are there at that time. Now, this is a very, I would say, an equation, a type of equation that comes up in many cases. Ralph James tells me that when he was discussing the heat loss from his bathtub, he in fact had the rate of change of the difference in temperature between the bath and the surroundings was proportional to the difference of that temperature. And so it's the same equation, and the solution to that equation is just that the number of particles at any time t is the number of particles you started off with at time t equals 0 times this so-called exponential function, which is falling off with time. There's some constant lambda times time. As time gets larger, this term, this exponential term, gets smaller, and so the number of radioactive nuclei that are still there, that are still non-decayed, is going down, 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 down. The important thing on this slide, however, apart from the mathematics, is the activity. The activity is the number of radioactive particles, the rate of change of radioactive particles. So many disintegrations per second. Now, we're going to introduce the concept of half-life. The half-life is the time at which the number of radioactive nuclei left is half what it was originally. So the number of particles half of what it was originally, and so you can set the exponential minus lambda times this half-life time equals a half, and you use natural logs, and you find out that you can calculate the half-life once you know lambda, or vice versa, because the right-hand side is just log, natural log of 2, which has a value 0.693. Now, half-lives of radioactive substances, when you've read about radioactivity and the big debate about how to get rid of radioactive material, you know that there are some with very long half-lives, that is, they take long time to decay, and there are some with very, very short half-lives, 10 to the minus 23 seconds. And for medical physics people, this is important. If they're going to treat you, radiotherapy, with an isotope that has a very short half-life, they better make sure that they get that isotope from wherever it's produced and use it before it decays away. Okay? So half-lives are very important. Here's the graph from your textbook. We start off with a kilogram of radioactive material, and it has a half-life of 16-20 years. In other words, I think it's radium. And if you go 2 half-lives, the amount that's left is 1 over 2 squared, what you had originally. And if you go 3 half-lives, the amount that's left is 1 over 2 cubed of what you had originally. So that's something, so even without knowing anything about exponents, you know in principle how to deal with half-lives, okay? 1 half-life, a half of what was there originally, 2 half-lives, a quarter, 3 half-lives, an eighth, 4 half-lives, what is it? Good, great, 16th, okay? So here we've got a simple little question, just like that. We've got a certain isotope with a half-life of 10 years. This means the amount of that isotope remaining at the end of 10 years will be 0, 1/4, half, the same. Half, okay, exactly. Now this is slightly different. I've put the question in another way. We've got a doubling time, but it's the same concept. So here we are, a number of neutrons in the reactor starting up, doubles each minute. So each minute, from 1 minute to the next, you double the number of neutrons. It reaches 1 billion neutrons in 10 minutes. When did the number of neutrons reach 500 million? And I haven't got an A, B, C, or D there, so 5 minutes, 6 minutes after the reactor starts, 8 minutes, 9 minutes, 0 minutes, 1 minute. I haven't got the slide with the answer. Okay, think about that and we'll talk about that next time. Oh, I have, I'm sorry. 1 minute, 2 minute, 5 minute, 9 minutes. Come on, you know the answer to this. 9 minutes, exactly. So now the last little bit I've got here today is that what happens with radioactive decay is we have a whole lot of reactions that follow on from each other, and we call these decay series. So you start off from uranium-238 with a very long lifetime, similar to the age of the Earth, and so half the amount is left, roughly. Though through several steps it goes to lead, which is stable. The series replenishes radium. Radium only has a half-life of 16-20 years. Now, if we'd started off at the beginning of the world with a supply of radium, it would have all gone by, or would have essentially all gone by now. But it's continually replenished by the sort of process